Recording. And for the purpose of the recording, we're going to go through the TUT memos. So we'll start with the class test 1 2 weeks ago, and then we'll do class test 2, which you did last Thursday. So this is to draw hot and cold composite curves. You need to use do the hot streams and the cold streams separately, of course, so that you can draw the diagrams. And what you're looking for is coordinates for the hot and cold streams. Now, right, when you look at when you draw a hot stream, you know that it's always going to be, because cooling water is described over there. You can start your hot stream at 0. Because the blue stream will never go past 0 compared to that hot stream. So the first thing you'll do is list the temperatures. Now that you've done a problem table, you will recognize this technique, that you first put down where are all the temperatures on the graph that you want to draw. So 200, 170, and 70 is the same for both streams. So there we go. 200, 170, and 70 are the 3 different temperatures we must look at. And then we have a look at what is the enthalpy change going from 200 to 170. So we need to see how many streams are involved. And from 200 to 170, there's only one stream involved. It's H1, and its CP is 4. And if we look at going from 170 to 70, that would involve both H1 and H2. So it will be CP of 4 plus 8 is 12. And the temperature difference from 200 to 170 is 30. Let me just get my comments up on screen. Yep, there we go. I can just catch comments when they come in. So the DTs are easy. There's 30 degrees difference there, and there's 100 degrees difference over there. And then you can work out the difference in the enthalpy going from there to there. So now you can start with the enthalpies by starting at the bottom. Remembering what you're trying to do over here. You need to figure out, you need to land up at 1320. So if we look at this thing, I just put in a 0 there. Then I added this enthalpy to go from 70 to 170. I added that enthalpy change. So there you can see F2 is there. So I'm adding the starting enthalpy 0. I'm adding 1200, and we're getting to that answer 1200. And of course, this is going to be exactly the same. We're going to add 1200 to 120 and get 1320. So if we look at that one's formula, 1200 plus 120 gives us that answer, 1320. And what that does is it allows us to change this. We can start our red line where we like. Let's start it at 30. And automatically everything will move on horizontally, essentially, by 30. But we know that the red line is always going to be the leftmost line, so we can happily start it at 0. But that is optional. You can start that where you like. And in fact, in the TUT, I said that you start at 1320. Yes, I actually remember now. The actual question said you start at 1320. Then you can work from there. 1320 minus 120 gets 1200, and 1200 minus 1200 gives 0. And you'd still get to the same answers. Okay, I actually copy the temperatures over, because then you can choose this whole thing and then say draw an XY chart. It just makes it easier to draw that way. And so that's just a little tip you can put the t's, which are the y-axis, then you've got x and y in the right order, and then it's easy to draw the chart. Easier to draw the chart. Okay, that's it. Cold composite curve. We've got four different temperatures: 200, 150, 80, 50 in that order. 200, 150, 80, 50 in that order. CP from 200 to 150. CP from 200 to 150 is only involving C1, which is CP of 6. So that's correct. From 150 to 80, we've probably got both streams. From 150 down to 80, this stream is involved and that stream is involved. So that's 11. And from 80 down to 50 is only C2, and that's got a CP of 5. Temperature difference, easy to work out. And then the enthalpy difference, of course, is the CP times the difference in temperature. And that is, all of these three columns refer to in-between lines. The values that are in between 200 and 150, in between 150 and 180. And then as soon as we go to enthalpies, we are going to start at, so cold starts hot, and all right, in this case, I've worked from the bottom upwards. I started at a 250 and I added the 150 to get 400. 400 plus 770 equals 1170. So I still did it upwards, the same as I did the hot stream. It doesn't really matter, even though you know the cold stream. Oh, the cold stream is getting hotter. That's true. No, so that one is the right way around. I did this one the wrong way around. The hot stream is flowing in this direction, but it doesn't matter to work it out in the opposite direction. Makes no difference. Get the same answers. Okay, and then I copy the temperatures, and then you can get your temperature profile. And then you need to do linear interpolation. You have to look at which is the smallest slope here, and that slope is 11 versus 12. The hot CP is 12, which is a smaller slope. And that will tell you whether this difference from that point to that point is bigger than that difference from that point to that point. Now, actually, this one is the bigger one. So this is the actual interpolation you've got to do, because that's the smallest temperature difference at that point. So you take from 1470, you go from there to there, 1470 to 1170, it's 300 kilowatts, and it is 50 degrees C difference. So we're getting the slope of that line, 50 degrees C difference, and then 30 kilowatts from the red line. It's 1200 and 170. 70 on that, yeah, and 155 is the, should be the linear interpolation, isn't it? Yeah, 5 degrees, 30 kilowatts compared to 300 is 0.1. That you're going from this point, it's 170 to that point in the enthalpy. This enthalpy is 170. That enthalpy is 1200. So we want to see going 30 kilowatts this way along this cold line. What will that number be? So it's 30 kilowatts. It's 0.1. It's 10% of the distance across there, because that was 300 kilowatts. And that would be 5 degrees, because it's 10% of 50 degrees C is the 5 degree. So that's just, but you've done linear interpolation until the cows come home. in your previous year, so I don't have to show you how to do the linear interpolation. So that answer there, that position there is 155 on the cold composite curve, and 155 degrees C, and that temperature there is 170 degrees C as it stands. So for 15 degrees, that would be the answer, 15 degrees delta T min. And for 10 degrees, you'd have to move this one. You'd have to go another 30 kilowatts, because we went 5 degrees going from there to there, and if we wanted to, and that would give 15 degrees difference, and if we wanted 10 degrees difference, we'd have to move this way by another 30. So we would change the 250 to 220. And yeah, that becomes 10 degrees, 160 degrees, 170, and we've got the 10 degrees answers. Okay. So this might have been a bit daunting when you did the TUT, but now that you've done the problem table, you'll see it's a little bit easier. And maybe this, having done this on the first TUT, maybe it sort of helped you understand problem table a little bit better. This thing of getting all of the unique temperatures first before you can proceed further. Right. So let's close this. No, we open up. We open up the other CPS 420 composite curve problem table hen memo. That looks like the right one. Okay, so you'll see at the bottom here, I've got. Let me just get rid of this thing so that I can see what you see. Yes, you can see. At the bottom here, we've got question 1 and then question 2. So let's look at, so we are on question 1, which is the problem table. Okay, so for the problem table, I've shown how to do the hot composite curve up here. But that's just so that I could to illustrate the hot and cold composite curves of the problem. Now I'm going to take right. We're going to use a delta T min of 10. So we're going to take 10 degrees off all the hot temperatures, because we want to bring this down. We want to bring this this red line down so that it meets the blue one, because then it's easier to solve mathematically. And what I mean by easier to solve mathematically is where we're going to be searching for a 0 in the sum of the enthalpies. So by taking the temperatures of the hot streams down by delta T min is 10 degrees C. I should have written it down somewhere. Anyway, this is one for D9. I've got it. D9. There we go. Delta T min. Okay. So those are all you can see up there. It is B4 minus D9. B4, let me use the F to show you where the formula is coming from. We're taking that temperature minus delta T min equals that temperature. And so that's for all of the hot temperatures. So that's the most important part. The very first thing you do in a problem table is to subtract delta T min from all of those hot temperatures. Okay, and this is where we start with this is essentially where we start with the problem table. These are our temperatures. We found out which are the unique temperatures, and the hottest there is 200, and we list them. I'm using the alternating lines this time, just to make it easier to see which of these are in between values and which of these are at a certain, which of these things refers to as at a certain temperature. Okay, 200, 190, 160, 150, I don't understand, Yuri, to list from hot to cold. Yuri, can you maybe talk to us? Otherwise, DH doesn't work as it should. To list from hot to cold. Oh, yes,
So,
yeah.
yeah.
Yes,
Yeah.
these things must be from the hottest to the coldest. Thank you, Yuri. Yes. Yeah, you see, when I give a lecture, it just seems obvious to me. But people doing it the first time, you start to realize. Okay. Yeah, that's why I'm searching out the hottest first, so we can put it at the top of the list. And so 200, 160, 150, and then we've got 80, 60, and 50. 80, 60, and 50. Right. And then we can start shading where does H1 go from? 190 to 60. H1 is from 190 to 60. H2 goes from 160 to down to 60 as well. 160 to 60. Cold, 80 to 200. From 80 up to 200. And the other one is from 50 up to 150. From 50 up to 150. Right. And now, at last, you can do DT. That's easy enough. Directly those temperatures. And now you can do DCP. So this one only involves C1. This range only involves C1. And C1 is 6. But don't forget to make that a -6. Cold temperatures must be minus. This one is cold, is plus H1 minus C1. Plus H1 is 4 minus 6 equals -2. Let's see if I've got, yes, I have got a formula there. Oops, wrong one. There we go. Okay. And similarly, this one is H1 plus H2. This one is this interval here, plus H1 plus H2 minus C1. And escape this one. Again, the wrong button. All of them. H1 plus H2 minus C1 minus C2. And now we're eventually losing out on C1. So we've got plus H1, plus H1, plus H2 minus C2. And finally, we've only got C2, and that is, oh, yes, -5. I was looking at the 10 here. Right. C2 is 5, but it must be minus because it's a cold stream. And this is where you can most easily make your mistakes. So that's why when you now multiply the delta T with the DCP, and you get all of those H's, when you add up the H's, start at 0, minus 60 equals 60, minus 60 minus 60 is minus 120, minus 120 plus 60 is 60, it's still minus 60, sorry. Minus 60 plus 70 is plus 10, plus 10 plus 140 is plus 150, minus 50 is 100. And now you have to go and check. There's my 100. Here I've added up all of the hot enthalpies. There are those adding up those two Q's, 1320, yep. And here I've added up these two. That's 1220. And the difference, of course, is 100. So there's more enthalpy in the hot streams than in the cold streams. So we're going to need more cold utility than hot utility, because we need to cool down hot streams. We need to cool down more. We need more enthalpy to cool down the hot stream than we need to heat up the cold stream. So we need more cooling water than steam by 100 kilowatts. So again, you have to check that to make sure that you haven't made a mistake here when you worked out the DCPs, delta CPs. Okay, so now you're fairly sure that you got these right, and now what you have to do is to have a look which is the smallest number here in this list, and the smallest number is 120. And if we're going to be finding this, remember we've used all the enthalpies have gone down by 10 over here to draw this graph. And now we're summing enthalpies starting from the highest temperature. We're looking at all the enthalpies that are involved. And when we get to 0, then we would have solved this thing where these two are touching. So what's happening is we need to say that minus 120 must be 0. And therefore we need 120 kilowatts of steam, of hot utility. We put a 120 there, minus 60 is 60, 60 minus 120 is 0, 0 minus 60 is 60, 0 minus 60 is 60. Where should we be plussing? 120 minus 60. 0 minus 60. What's going on here? Well, the other way, yeah. The other way of looking at it is we adding 120 to each of these numbers. So there, from 0, we added 120. So therefore, we must add 120 to all of these numbers. Minus 60 plus 120 is 60. Minus 120 plus 120 is 0. Minus 60. That should be a 0. That should be 60. Yes, no, that's right. Okay, I'm getting a whole lot of Slack messages that are unrelated. It is 60, yes. And that one works out right. And 270, 120 onto one, yes, right. And then that's your cold utility. 100 plus 120, 220. And now again, you can have a look. 120 for hot utility, 220 for cold utility. It is 100. The cold is 100 bigger than the hot utility. So again, make sure that you check that so that when you submit your answer, you know you've submitted correctly. This is how the marking occurred. That you've worked out that 100 kilowatt enthalpy difference. Can you guys hear these notifications on my microphone? Oh, good. There's a whole InterVarsity brewing conversation going on in Slack, and it's disturbing me. Okay, I'm glad you're not hearing the notifications. So this is how I would allocate temperatures, allocate marks there that you showed that the 100 difference, enthalpy difference, and that you've got the correct temperatures, 7 discrete temperatures, 30 degrees C, the temperature span, second value, oh, I see. Oh, this is when I asked questions. Right, this is from the previous year. In your case, I only asked 7 questions. In the previous year, I asked 15 questions. Okay. So that's just being able to read them off the graph once you've done that. Right, so now we get to the more difficult part of the lecture. And that is designing a heat exchange network. All right. So we know that the cold pinch is at 160, and because delta T min is 10 degrees C, the hot pinch is at 170 degrees C. So there's cold pinch, and we know how much is hot utility and how much cold utility. Right, that's the MER values. So we can write out our H1, H2, and now this is back to the original temperatures, of course. It's not the temperatures minus 10 degrees C for this design your heat exchange network. So we put in all of our H1, H2, C1, C2, and we draw the horizontal lines, and the temperatures, we know where they start and where they end. So we can put in these 270 degrees C, we can put in the 200, 170. C2 doesn't get to the cold pinch temperature, which is 160. So you only draw it until before this to make sure it's all correct. Can you zoom in? Yes, of course. Good idea. Thank you. I have to recognize which are Slack notifications and which are Blackboard notifications. Okay. Now, sorry. Thank you, Eric. That is much better. Okay, so the C2, we're not going to draw the horizontal line right through because otherwise we're going to get confused over here. We see that it only gets to 150 and the cold pinch temperature is 160. Right, cold one starts at 80 and goes to 200, so we can draw that right across. Okay, draw in the pinch. Boom, there it is, 160, and therefore we can now write in our temperatures for the hot because we know we are going to start against the pinch as far as putting in the heat exchangers. So let's start with the easy one. CP hot must be less than or equal to CP cold on the hot side. And we look at CP as 4. Hot side. Oh, right. Yeah, we could have put this, that's true. We could have put this square right up against this pinch here and just drawn it over here. Just so that we know there's nothing happening here. We don't have to do anything. It would have made it more clear. Yeah. So we do only have two lines, one hot stream, one cold stream, and now we must check if the hot stream is less than or equal to the cold stream. If it's not, we're going to have to do stream splitting. So that hot stream is less than the cold stream. And so we can put in a heat exchanger. We can work out how much enthalpy is available over here. Going from 200 to 170 is 30 degrees, CP of 4, 120 kilowatts. Over here, we've got 160 going up to 200, that's 40 degrees, and CP6, so that's 240 kilowatts. So we have a look. That one was 120. That one, we need to add 240 to this cold stream. And so we will use the smallest number. We don't want to subtract more than 120, otherwise we're transferring heat across the pinch. So that's 120. And then, of course, to make up the 240 required to heat up the stream, we'll use our steam, which is 120. And yes, it is the same as the MER that we've got on the previous page. Let's quickly go to the previous page, and there it was, 120. Okay. So that's done. We finished on the hot side. Now we look at the cold side, and on the cold side, we have to start against the pinch with CP hot greater than or equal to CP cold. So CP hot must be greater than or equal to CP cold. There's only one cold stream, and that's got a CP against the pinch. There's only one cold stream, and that's got a CP of 6. So we have to find a hot stream. The only hot stream that we can interchange with is is that one, against the pinch. Against the pinch, that's the only cold stream, and that is the only hot stream with a CP higher than it. So that is the only match that we have. Okay, now we can go and work out how much energy is required to go for this cold stream to heat up from 80 degrees to 160. And that's 480 kilowatts. So we would write 480 there because this one is a lot more than 480. It is 100 plus 300 is 400, and 400 is 800. Let's just check that. 170, 70, 100 degrees, 800 kilowatts. To cool down this hot stream, we need 800 kilowatts. So we choose the smallest of those, and it would be 480. All right. I'm going to go. Yeah, Philip.
Sorry, Prof, but if you say we would select 480 and that's a correct approach, why is it 400?
Yes, I'm getting there, and that's why I'm looking down here. This is where I do my calculations, and so as soon as I do a 480, I'm just looking at how this is structured, so that I can show you what you would do, what you would be doing. Equals H14 equals H14. Oh, okay. So this one I can change 480. Right. I'm just checking that the temperatures relate. This one. No, the temperatures haven't changed. If I make this 480, that becomes 110 degrees C. All right, so that temperature there, this is the live spreadsheet. This is the live spreadsheet that shows that's 110 degrees C. As soon as this is 110 degrees C, the very next heat exchanger you can put in is going to be this one. And then you have a look at how much you can subtract using this one. It'll be 500 over here, and this one you'd be able to subtract 120 plus 80 is 200. That's 200, 400. So there's 400 kilowatts in this stream, and there's 500 kilowatts in this stream. Okay. Now, let me just think. $170. That's right. That's right. So on this side of, if we make this the next heat exchanger, on this side of the heat exchanger, you've got 170 degrees C and 150 degrees C, which is 20 degrees C difference. Now, when you have a look at the CPs, luckily it's not against the pinch. That's why you need to have, because CP hot is less than CP cold. And when it's less than CP cold, you know that on this cold side, when the CP hot is less than the CP cold, you know that the temperatures are going to get closer to each other on the other side of this heat exchanger. So we've got 20 degrees over there, which means that it's not against the pinch. It's 20 degrees. Therefore, it is you've got some leeway for the temperatures to get closer. So you put in this heat exchanger, and you have to work out how many kilowatts can you put in over here until you eventually get to the 10 degrees C on the other side. So let's have a look at that heat exchanger. 200. Let's just check that this one refers to J18. Yes. So I should be able to change this one. And if we try 500 degrees, 500 kilowatts, because I think we said this one is 2 plus 2 is 4. This one was 4, all right, 400 kilowatts. Smallest of these two. This, here I'm pointing with my finger. This one was, this stream is 500 kilowatts. This stream is 400 kilowatts. So we would first try 400 over there. At 400 says that the temperature on the other side of this heat exchanger goes to 70 on both ends, on both heat. So this would go to 70 and that would go to 70, and then you have a delta T-min violation. So instead of 400, we choose 300. You see now we've got 5 degrees C temperature difference. So if we want another 5 degrees C temperature difference, we would choose 200. Okay, now you could have done the maths because you just needed to find out, this is X, and whatever X is, you'd be able to work out this temperature as this temperature difference, this temperature and that temperature, given a certain X. And you needed to make sure that it's two simultaneous equations where these two must be equal to 10 degrees C. This 120 minus 110 must equal 10 degrees C. And then you can solve for X for that enthalpy. Or if you've got a spreadsheet, you can do it like I've been doing it and come out at what is that? What is the maximum enthalpy you can subtract from the stream so that you don't get your delta T-min violation on the other side of the heat exchanger. Okay, so now we've got 110 degrees C here. Now we have a look at the next heat exchanger that we would like to put in. We still need to get rid of 300 on C2. So if we make this the next match, now we have a look at this 120 degrees C. It's not 120 degrees C. We made this 480, and this is 110 degrees C now. That's 110 degrees C, and that's 110 degrees C. So we realize if we want to make that match, we should make this at least, this matches where CP hot is bigger than CP cold. So the temperatures are going to go further apart on the other side. So all we have to do is get this to 120 degrees C, and to get it to 120 degrees C, we have to make that, you see there it shows it's 110. We change this to 400, and it changes to 120 degrees C. Now we've got 120 degrees C and 110 degrees C. Now we can put in that heat exchanger. Okay, so you can see this is design. You have to logically see which would be the next possible match, and then you've got to use this thing that we described in the lectures called looping. The looping means decreasing the kilowatts of your heat exchangers so that you don't get a delta T-min violation. So this 120, I'll just copy it, Control C, Control V, so that we can start at least at 10 degrees C. We know that the match between this one and this one will mean a bigger temperature difference on this side, and it is. Okay, so who's been talking? Shouldn't you then start the analysis between H1 and C2? Let's have a look. H1 and C2. H1 and C2. No, because that's not against the pinch. You have to always start against the pinch. So start the analysis with that one. You place this heat exchanger against the pinch, sure. there was nothing wrong with placing this one first. Then you start looking at other heat exchangers that are now not against the pinch. So this wouldn't be the right procedure to put this heat exchanger in first. Then we see how much we can exchange H2 and C1 to ensure that So that's essentially what we're doing. We had to make that match. That was the only match that was possible against the pinch. So you always do against the pinch first. Then later we saw that this could have been done before that time, but then the next one that you'd put in would still be this one. So yeah, once you got both, you can go onto your next match, and then you see that you have to, this temperature had to be a little bit higher so that you could actually make that match and reduce that from 480 to 400. This one we had to reduce from 400 down to 200, from 500 down to 200, so we could get the right temperatures across there. And now eventually we're making this match starting at 120 and 110, and we use the rest of the 500, which will be a 300 kilowatt heat exchanger, and the temperatures are okay on the other side. This one is now complete. We can tick that off. This one, we can just use cold utility. In fact, both of them are not ticked off yet. So let's not worry about cold utility yet. We have a look at which next heat exchanger, because we've got to remove all of the heat from C1, or add all of the 480. We've only done 400 because we can't add hot utility onto the cold streams on this side, on the cold side. We're not going to add hot utility. So we put in our 80. We put in a heat exchanger with C1, and what are we going to exchange with? We've got 120 degrees C on this on this stream, and this one is 93 degrees. So that's a possible. It's far away from the pinch. So we can make that thing, but we wouldn't be able to make it over here. That's 82 degrees. This one is 93 degrees. The cold stream is hotter than the hot stream. So we wouldn't have been able to make a heat exchanger here and there. This is the only match that's still possible. 120 degrees, 93 degrees, and it doesn't matter that the CP of the hot is less than the CP of the cold. Because we've got more than delta T min on this side. So the temperatures are going to get closer to each other. 80 kilowatts is what we needed over there. 80 kilowatts would bring this to 100, and we still got 20 degrees C difference from there to there. So they have got closer, but not so close that we get a delta T min violation. If we did get a delta T min violation on this side, we'd have to reduce this one until we get exactly delta T min difference there, and then we'd have to have more exchanges in this heat exchange, in this heat exchanger design. Right. So now we've taken away we've added the enthalpy to both of the cold streams. We don't have to add steam, and we're not allowed to add steam, so that both of these cold streams are ticked. Now we can just see how much extra energy we must remove from these hot streams, and that will be 120 there and 100 there. Add them together, 220, and yes, we're happy that 220 is the correct answer from our MER. And now you've got something that works correctly. Okay. It's very easy to, with this heat exchange network design, I wish I knew how to get rid of these controls that suddenly pop up. Okay, never mind. It's very easy to miss delta T min violations. So that's probably what you found in your TUT, that when you started designing this heat exchange network from scratch, that you might have put in 500 over here, 400, you might have put in 400 over here, and missed that those two temperatures are the same. It's very easy to do. So every time you put in a heat exchanger, check both sides. There, 160, 170, this one, 120, 93. Okay, tick. And when you check, you don't just subtract the two. You have to make sure that the hot temperature is hotter than the cold temperature. Now you go on to the next one. 170 degrees, 150 degrees, that's fine. You go on this side, 110 degrees, 120 degrees C, that's fine. So you've got to do this laboriously. Take this one, 120, 110, that is hotter than that one, about 10 degrees. This one and this one, no problem. Okay, so yes, do that laboriously. I believe that lots of people missed this temperature difference. Yeah, they put in 400 over there and these two are the same. I think if you used 400 here, let's just have a look. Yeah, 70 and 70. Very easy to get wrong. Okay, so when I mark these things in the exams and the tests, I think Natasha might be a little bit more lenient with you. I always mark, if you've got, as soon as you get something that is wrong, you've made a match that is not against the pinch. In other words, you haven't started against the pinch with a match that meets this criterion. So if you've made this match and you've said 480, I give 1 because you've placed it at the 1 mark for placing it at the correct place, and then you won't get the mark for 480. If you've already changed it down to 400, then you'll get both marks. And then I go on to the next exchanger that you place, and 1 for the placement and 1 for the kilowatts. And then I go on to the next one, 1 for the placement, 1 for the kilowatts. So as soon as you make a mistake, then essentially you don't get any more marks further downstream. As soon as you've made a mismatch or a delta T min violation somewhere, you don't get any marks for further heat exchangers on that heat exchanger network design. So very important to follow this principle of making the matches against the pinch correctly and then working away further. And then of course this concept of looping where you need to change down, reduce the kilowatts, the duty of heat exchangers, working from the pinch, away from the pinch, you start reducing these. You have to go back and reduce them so that you can still make matches correctly. Okay, that brings us perfectly on time to the end of the lecture. Is it necessary to show the steps? No, I just want to see this diagram. You draw the diagram, and that's it. So certainly in the exam, just like this test, I wanted you to actually draw it on paper. It's much more difficult drawing it in Excel or in PowerPoint. So I'll be able to see if it's correct. It's nice and visual and graphical. It's easy to mark in that respect. But yes, when I mark, I actually set up a spreadsheet like this, so that when I change these numbers, I see that. And then what I do in my marking spreadsheet is I give the delta T min, the delta T, I will work out over here in this column, I'd give the 170 minus 160 value. That'll be 10 degrees there. And I'll give the 120 minus 93.33 value over there. And then I'd be able to quickly scan across. So then if somebody goes and does a certain arrangement, I can quickly put it in and put in the values, and I'll quickly be able to see where the delta T-min violation is if it's wrong. But there are also other ways of other arrangements of these heat exchangers, which you can do. So when I mark, I actually have to make all of the variations. I have to make a little spreadsheet like this with all the variations, so I can see some of the variations in the order of these heat exchangers is impossible. So somebody presents it and they think it's correct, but then I've got to actually enter it and then see where the delta T-min violations did occur. All right, I'll see you guys tomorrow then, and then we'll carry on with the course, with the modules material.